first webinar, what we covered in first webinar. In the first webinar, we did present about the basics of nanoindentation, particularly how one can do nanomechanical testing with the instrument indenter, where you bring a diamond probe, apply a force onto the sample surface, and measure the load displacement response through the transducer. And from that load displacement response, one can measure the stiffness of the material by taking the slope of the unloading curve. And from knowing the stiffness of the unloading curve and knowing the geometry of the probe, one can calculate the modulus of the material and hardness of the material. Hardness is nothing but the maximum load you apply divided by the projected area of contact. Area of contact can be computed by knowing the indenter geometry and the area function that you calibrated. And for the modulus, you need to know what the stiffness of the material that can be measured from the unloading slope of the load displacement curve, and with the known area that you calculate from the area function, you can calculate the modulus of the material. This is the basics of nanoindentation technique, and this is the quasi-static nanoindentation technique. Okay, and I also mentioned in the last time that the load displacement curve that you get is unique to the material that you test, depending upon how elastic and elastoplastic it is. So you may get an elastic response or elastoplastic response, and we call it as kind of an indentation curves as a fingerprint of the mechanical response of the material. And I gave, for example, the fused quartz is the standard material that we use to calibrate the indenter tip. You can see the load displacement curve, and you can see the shape and size. And then if you compare with aluminum, it's totally different. In fused quartz, you get more of an elastoplastic, but more elastic recovery, whereas in aluminum, you see more plastic deformation. And this is also elastoplastic. But if you look at the polymer material, the shape of the curve is totally different. And one particular thing that if you notice here is that, and this particular experiment was done in a displacement control mode, where you load up to a load and keep the displacement constant. And then if you try to do that, you can see the load drop as you try to keep the displacement constant. Okay, and this is particularly mainly because of the creep on the sample that you can also see on aluminum, whereas you load and try to keep the load constant, you can see there is a continuous increase in depth of penetration. Okay, this is what I'm going to focus today. So when you have materials that exhibit creep and viscoelastic mechanical response, how you can calculate their mechanical properties. Okay, and this is what I'm kind of showing in a very simple slide. This is done on a PMMA polymer material. You can see the typical load displacement curve, but at the maximum load, when the load is kept constant, you see increase in penetration depth, and this penetration depth is due to creep. And now when you unload and reload, you can start to see a kind of a hysteresis develops in the load unload curve. Whereas, for example, if you do it on an elastic material, when you load, hold, and unload and reload, it will retrace this curve. That's why we were able to use this unloading curve as an elastic. We can treat that unloading curve as an elastic curve and measure the slope of the unloading curve and calculate the stiffness. But when you have a viscoelastic material, when you load and reload, it will not retrace on that curve. So it is no longer elastic. It is almost like a viscoelastic. So that's why you start to see this hysteresis. And because of that, you will not be able to measure the properties if you use the standard methods that I mentioned in the past to measure the mechanical properties of the material. Okay. For example, I gave one example in the beginning where when you want to measure the stiffness of the material, you measure the slope of the unloading curve. When you have creep and viscoelastic response, you can't fit a slope, and therefore, when you try to use the standard method in measuring the mechanical properties, you will end up in error. Even materials with the less viscoelastic, you will see this problem For example, in this particular case, depending upon how much percentage of the unloading curve you use to fit the curve, you can see that the modulus of the material is different depending upon how much percentage of the curve that we are going to use. So these are all the problems that you see in standard analytical method that we use to deconvolute the mechanical properties. So how do we then do on viscoelastic materials or materials which have creep, how you can go and measure the properties? So this is what is being solved using dynamic mechanical testing, where in dynamic mechanical testing, what we do is, along with the quasi-static load that you apply and measure the displacement, you superimpose a small sinusoidal force and measure the sinusoidal displacement response. So, and that's what you can see as a small oscillation imposed on the transducer. And then this is a force oscillation amplitude, and then you measure the displacement response. So for example, if you do it on an elastic material, I kind of plotted two curves here, the red and blue. And for example, if you apply a sinusoidal force and you try to measure the displacement response, if you measure the same, and if there is no time lag between the force and the displacement, that happens for elastic material, there won't be any phase shift between this force that you applied and the displacement you measured. Okay, but if you do it on a viscoelastic material, you start to have some kind of a time lag, some kind of a lagged response with respect to displacement. So that lag is the phase lag that you measure, and it is characteristic of the viscoelastic material. Okay, so how do you do this? For example, you can apply a sinusoidal force, that's not a problem, and you can also measure the sinusoidal displacement. But if you try to do it when you're in contact with the sample surface, there has to be a kind of a limit to the oscillation amplitude that you apply, because if you do a large displacement, large force amplitude, as the tip oscillates, it may come out of contact. So your force amplitude has to be very small, and your displacement amplitude also has to be very small. So when you do that very small signals, when you apply very small forces and try to measure very small displacements, it's almost buried into the noise. So normal way that we measure the force displacement response is not going to work. So we use a unique measurement technique, which is a locking direction technique. It's a kind of a specialized locking. It's an amplifier. It's a vector amplifier, where we can apply a known frequency of force amplitude and measure the displacement response at the same frequency using locking detection. That helps us to measure the displacement response, even though the displacement amplitudes are very, very small, less than a nanometer. So we use a locking detection technique, and for applied force amplitude, we can easily measure the displacement amplitude. Along with the displacement amplitude, we can also measure the phase lag that I talked about between the force and the displacement. These two quantities you can directly measure from the lock-in amplifier, and from the measured response, you can deconvolute the mechanical properties. But before we doing that, you need to have an understanding here, because when you apply a sinusoidal force in terms of to the transducer, it goes through an electronics, force electronics, that kind of has some contribution, how the electronic response as a function of frequency. Then it passes through the transducer and applies the force. Then it goes to the detection electronics to measure the displacements. So you kind of have an instrument response along with the material response that you wanted to measure. Okay, along with the contact stiffness or the damping, particular to the material, you also have the electronic response, the transducer response. So you have to deconvolute the actual mechanical response of the material by knowing what the electronics is doing, what the transducer is doing. Because we built this instrument, we know what the electronics we are using, we know what the constants that needs to be used to deconvolute the electronics response. We also know the critical parameters of the transducer, for example, stiffness of the transducer, damping coefficient of the transducer. This transducer has a three-plate capacitance structure. I already kind of explained in the last webinar, but the central plate is kind of suspended with a spring. When it oscillates, you do have air. These experiments are done in air. So when the air is there in between these two plates, it kind of damps this transducer. So you have a kind of a damping coefficient associated with the transducer. So you need to know what the damping coefficient is. You need to know what the spring stiffness is. I mentioned that the center plate is suspended by a spring. So the spring also has a unique stiffness. So once you know all these constants with respect to the transducer and the electronics contribution, from the measured response, you can disconvolute what the material response is. So these are all the important steps that you have to do. So to deconvolute this response, you can model the transducer as a simple harmonic oscillator. And this is just a first year physics. For a simple harmonic oscillator, if you know what the mass, if you know what the damping coefficient, if you know the force amplitude, you can kind of rewrite the whole equation in terms of displacement response. So you know what the force that you are applying, because that's the quantity that you're applying. This is the displacement amplitude you can directly measure from the lock-in amplifier. These are all the constant that I mentioned. This is K is the stiffness of the transducer spring that I kind of shown schematically here. And you know the mass of the transducer, and the damping coefficient is something that you can calculate through this calibration. So once we know all this parameter of the transducer, the electronics and all those things, you can measure the response by making the contact, the tip in contact with the sample. And then in the previous example that I shown, you can measure the response. This is particularly for the transducer response. If you plot as a function of frequency, if you try to measure the amplitude, you can see the resonance happening at some particular frequency. And also, if you look at the phase shift, there's a huge phase shift during that resonance. Okay, so this is only for the transducer before making contact with the sample. And what it says is basically the transducer is very sensitive at the resonance. So if you try to do the experiments closer to the resonant frequency, the transducer is very, very sensitive. Okay, and we can use that fact for a difficult, for example, if you want to make ultra sensitive measurements, you can run this experiment closer to the resonant frequency, and then try to come in contact. And in such cases, you don't have to apply a very small force. You don't have to apply a very large force. You can apply a very, very small force, but because of the resonance, you have higher sensitivity, and then you can make use of that sensitivity to do very sensitive measurements. Okay, so but also because we know this transducer response, it is kind of a simple harmonic oscillator, we can fit this whole equations and try to deconvolute this constants that I mentioned by fitting this curve. And that's another way of figuring out what the spring stiffness is, what is the mass of your transducer, what is the damping coefficient. Okay, so and then the only unknown here is basically what is the stiffness of the contact. That is what you wanted to measure. This contact stiffness in quasi-static indentation technique, you measure by taking the slope of the unloading curve. Now here we are measuring through applying a sinusoidal force and measuring the sinusoidal displacement. That is the big difference between quasi-static indentation testing and dynamic indentation testing. In quasi-static, we need to progressively load and unload and measure the stiffness from the unloading slope of the load displacement curve. In dynamic testing, you can measure this stiffness continuously as you indent. Okay, that brings a lot of advantage, and I'm going to go and give you an example of that. Before that, I also wanted to kind of give you an idea of what else you can measure with this technique, because we can apply dynamic force and measure dynamic displacement that allows us to measure what we call the viscoelastic response of the material, particularly the storage and the loss component. This is kind of a schematic that explains, for example, in a typical low displacement curve, this curve I already presented for PMMA. You can see if you take the low, if we take this low displacement curve and try to integrate the area under the curve, the whole curve, that kind of gives you the work is being done to create the indent. Now, when you unload, some amount of this work is been, the energy has been released. That is the elastic energy that has been released, okay? And this is the energy that the hatched area that you see is kind of the stored energy into the sample. And this is what it gives rise to residual stress in when you do the indent. And this stored energy can be directly measured by taking the area under the curve, okay? And if you measure this energy by integrating the loop That gives kind of the last image. Okay, so you have kind of a storage and loss component when you do this mechanical measurement, and we call that the storage and loss model. We can associate that with the storage and loss models. In a simple analogy, it is something equivalent to this. For example, let's say you have a rubber ball, you're kind of trying to bounce onto the floor. When you try to drop it from a height, it doesn't recover to the same height. It recovers to some kind of a height, and depending upon how much it has been lost. So similar to that. So you have a kind of loss component and storage component. If a viscoelastic material, we call it loss modulus and storage modulus. And now with this dynamic measurement technique, you can directly calculate the loss and storage modulus by measuring by the stiffness and the damping coefficient of the material. And if you take the ratio of the two, that gives you tan delta, which is another parameter that characterizes the viscoelastic response of the material. So all this thing can be now measured by doing dynamic measurement technique. Okay. So again, to recap, there's a big difference between quasi-static technique and dynamic technique. In quasi-static technique, you measure the unloading slope of the load displacement curve. That gives you the stiffness of the curve. And from the measured stiffness and known contact size, you measure the modulus of the material. This modulus is what we call reduced modulus. And with the dynamic technique, you have two components, the loss component and the storage component, both of which can be easily measured by measuring the damping coefficient of the material through the lock-in detection technique that I just mentioned. And you can also measure the storage component of the modulus by measuring the storage stiffness and also knowing the projected contact size through area function calibration. Okay, so this is the main difference. In quasi-static technique, you just measure the elastic modulus, the reduced modulus, but in dynamic technique, you can measure both the loss and storage modulus as well as in tan delta. Okay, for example, if you do it on an elastic material, it gives another advantage. For example, in load displacement curve, when you try to do a quasi-static indentation, when you do one load displacement curve, you have only one measurement because you can do only one slope. You can measure the stiffness of the curve by measuring the slope of the unloading curve. So it gives you only one measurement. Whereas when you do the dynamic test, it's almost equivalent to load unload at each and every point. So throughout this load displacement curve, you can continuously measure the contact stiffness. So it kind of, you can, for example, if you want to measure the mechanical response as a function of depth, the dynamic measurement technique is very useful. You can measure continuously how the stiffness is changing. And from that, you can measure continuously what the modulus is, how the modulus is changing, or how the harness is changing as a function of depth. So this is what we call depth-dependent mechanical property measurement. We can measure it as a function of depth continuously with the dynamic measurement technique. Whereas in quasi-static technique, you do need to do multiple load unload indentation experiments. And there's a trick that you can apply, we call partial unload, where you can load unload in one single indent, but you need to do kind of a load, partially unload, and the reload and partially unload. We can do that, but even that kind of gives you kind of some kind of limits, how much of data that you can extract from in one single indent. Whereas in dynamic indentation technique, you can continuously measure this property change as a function of depth. Okay, so I'm going to give you a kind of one example. This is for an example of a combinatorial screening of material. What it is done here is, this is an example directly from one of our customer. And here, the process is basically to develop an alloy in a coupon format, a 2" by 2" coupon, where you can kind of have 44 different regions, and each cells that you see, small cells, is each small cell is basically a unique alloy combination. It's kind of a ternary alloy. By changing the composition of indium, zinc, tin, you can change the alloy composition by in sputtering target, and so that you can have a different alloys in a 2" by 2" coupon. So there are 44 different alloys in this coupon, and you can go and rapidly measure the mechanical properties at 44 different locations. That kind of gives you how the property is changing for different alloys. So here, if you try to do that in quasi-static indentation technique, for example, in this particular case, there were about 70 quasi-static indents were done for a depth from 15 to 100 nanometers. It typically took about 300 to 400 minutes by doing this quasi-static indentation technique. Okay, and then you can get this low displacement. We can get this harness and modulus. These points that you see is a measure of modulus for each low displacement curve. Okay, and this is what I mentioned. You can see that in the insert, you have multiple low displacement curves superimposed onto each other, and from each low displacement curve, you independently measure the stiffness, and from that you measure the modulus and then harness. Okay, so you can see the modulus and harness plot here. Okay, so same thing with the dynamic indentation technique. You can see you can continuously measure this property without, you can see that you can have a large amount of data, and you can do within 3 to 5 minutes. So dynamic indentation technique not only allows you to measure the viscoelastic mechanical response, even for elastic material, you can have a high throughput, high density data in a very short time. So that is the advantage. And it took only about, instead of taking 8 to 9 days to get to know about 44 region, it only took about 11 to 12 hours, and you have a better data with the dynamic measurement technique. This is what has been shown over here, and you can see that whether you measure it through quasi-static technique, that the large diamond red plots that you see is measured through quasi-static indentation technique, and all the other plots are through dynamic technique. This is for harness. You can see the trend and the measurement, they are pretty much the same, whether you do it through quasi-static technique or a dynamic indentation technique. But a dynamic indentation technique gives you kind of a high resolution data in a shorter time. So it's very, very advantageous compared to measuring just the quasi-static indentation data. So nowadays, most of our customers, even in our lab, we pretty much do dynamic measurement technique rather than quasi-static indentation technique. Same thing with modulus. You can get the same kind of a good quality data, whether you do it in quasi-static or dynamic, but dynamic has much higher resolution, and it can be done much faster. Okay, that is a big difference between quasi-static and dynamic technique. So with respect to this kind of an example where we are trying to figure out how the align combination, basically how the different ally formation gives you different kind of a mechanical response. So this is on a ternary ally diagram. You can see, for example, like along this line, you have this modulus measurement, and if you change the composition from 10, 20 to 100%, how the modulus is changing along this line from indium to zinc or from indium to tin. You can see that. So in a ternary ally diagram, you can superimpose the property that you measure. So instead of doing like in months and years, you can use this combinatorial approach to figure out what kind of an ally gives rise to what kind of a mechanical response, and what will be the right ally combination to choose the better mechanical property. So combinatorial material science is kind of a very, very advanced now, and this kind of measurement technique, dynamic measurement technique, it kind of helps us to do these measurements much faster in high throughput way. Okay, that's one example. This is particularly done on an elastic material. Okay, now, for example, another important example is thin film mechanical response. When we deposit thin films, what happens is basically when you try to do an indent on a film on a substrate, when you do the indent, and there are two zones of mechanical response you need to focus. One is the local plastic deformation, and this is the plastic zone, which is the smallest, which is the length scale is smaller. The plastic stress field varies 1 by r cube, whereas an elastic stress field varies 1 by r squared. So for a given load, the plastic zone size is much smaller, but elastic zone size is much longer. So when you have this kind of a film on a substrate, a kind of a state, when you wanted to measure the property, when you do an indent, because the elastic zone is much bigger, it will kind of brings the response of the substrate along the thin film. So that's why you have this 1/10 thumb rule, where if you wanted to measure the property of the thin film alone, you need to indent 1/10 of its thickness. So for example, if you have 10 nanometer thick film, you have to do within 1 nanometer depth and measure the properties. That kind of gives you the limits, right? So for thin film systems, it's kind of very difficult to do in quadratic indentation technique, but we have this dynamic measurement technique where we can measure this property continuously. That helps to kind of alleviate this problem. So in this case, if you try to plot the storage modulus as a function of depth, you can see that it is kind of changing from thin film to the substrate. You can see that the modulus is increasing. And then when you try to do at smaller and smaller depth, this is all done with this continuous the dynamic measurement technique. It kind of flattens out here. That gives you kind of a confidence. The particular response that you're measuring is due to thin film only. The substrate influence is not there. So even at depths like 10 nanometers and 5 nanometers, you can reliably measure the modulus of the material. Okay, so that's another advantage of doing dynamic measurement technique on even on elastic materials. Okay, so I'm now going to talk about the viscoelastic response of the material. And in this particular technique, which is called reference frequency technique, was developed by me many years ago as a part of my DPhil thesis, where what we do is like we can measure the property of the material as a function of frequency, but we do it on over a period of time, and that kind of gives another complication of thermal drift. So it will be very difficult to track the size of the contact. So we kind of developed a reference frequency technique where you use one frequency as a reference, where the mechanical response of the material is known. Then you change the frequency from low frequency to high frequency to measure the response of the material as a function of frequency. So the reference frequency kind of keeps tracks of the change in contact size without worrying too much about the drift, whereas the change in frequency kind of gives you the frequency response of the material. Okay, so if you have, if you want to have some kind of idea, you can also read. There are a couple of papers you can Google and find out. And if you need to know more about that, you can also send me an email. I can send you more details on this. This reference frequency technique is now kind of a standard for measuring nanoindentation based viscoelastic material. Storage and loss modulus as a function of frequency, and it's also been adapted for AFM-based technique. Now it's been used to measure the viscoelastic response of polymer materials by AFM as well. Okay, so with that and with the application of by varying temperature, you can also measure not only the frequency response of the material, but also the influence of heat and how the material is changing as a function of heat, as a function of temperature. And that kind of helps us to understand the time temperature superposition response of the mechanical response of this polymer materials. I'll come back to this a little later when I talk about high temperature experiments. So again, like this particular technique that I mentioned, measuring the loss and storage modulus using indentation technique, kind of new at that time when we introduced. So we wanted to kind of compare it, how it compares with the macroscale dynamic measurement technique. So you can see in this particular plot, the storage versus storage modulus versus frequency. There are two plots out there. One is by doing macroscale mechanical testing, standard macroscale DMA testing, where these triangular plots are for macroscale testing, and these circular plots, circular dots that you see is for using nanoscale testing by using dynamic indentation technique that I just presented. You can see how the trend is pretty much the same. And if you compare the tan delta, also you can see that it's pretty much comparable to macroscale testing. So this kind of gave us a confidence. This is the methodology and the measurement technique that we used to measure the dynamic and mechanical response kind of compares with macro scale. And to do that, actually, we almost went up to kind of a micron scale, because at true nano scale, the properties of materials may be different. So we kind of went up to kind of a micron scale and measured the mechanical response and compared that to macro scale. So even at micron scale, we were able to match the macro scale properties. Okay, and this is another example for example, if you have a amorphous polymer thin films. This is a problem. When you have bulk materials, there are ways to measure a viscoelastic response of the material, but when it is in a thin film form, it's very difficult, and there are no standard techniques like the macro or DMI technique won't be useful. So this particular measurement technique is very, very useful in those cases. So in this particular case, we were able to measure the tan delta, storage modulus, as well as glass transition temperature of the material. Okay, again, I will come back to that when I present the high temperature application. Okay, so now we have a robust measurement technique where we can measure the viscoelastic response. Can we use this, extend this technique for imaging as well? For example, in the first webinar, I presented a way to measure the surface morphology of the specimen that you wanted to do indent by scanning technique, right? So, where we just measure the topography of the surface. Now, because we can apply the dynamic load, along with the topography, you can also measure the dynamic response as you scan on the surface. And can we use this scanning technique to map the mechanical property? This again was part of my postdoctoral work many years ago, where we were able to do this by doing a modulation of this force on the transducer and measuring the dynamic response as you scan the tip on the surface of the sample. And with that, you were able to get the image, mechanical response in the image format, where you can measure the phase response or the contact stiffness response in the image format. And you can process this data to deconvolute the properties like storage and loss modulus as an image. So this kind of measurement gives you the power of doing many indent experiments. For example, this is an image of 256 by 256 points. To do an equivalent amount of to get equivalent amount of data, you may have to do like 40 days to get this particular image by doing one individual indent point by point, 256 by 256 point. Whereas by imaging technique, by simply scanning on the surface and applying the force and oscillatory force and measuring the oscillatory displacement, you can do this in 10 minutes. That gives you kind of the power to kind of look at the property as a map, and it helps in many situations where you can go and find this. And this is a very surface sensitive technique. So which means that if you wanted to understand how the near surface properties are changing in terms of mechanical response, particularly elastic response, you can do the simple modulus map, and then you can get this change in mechanical response as an image. That kind of gives you the idea how the properties are changing at different locations. Okay, this particular example is for a fiber epoxy composite, and you can see that circular things are fiber, and then the surrounding matrix is dark, just black. Okay, and you can see how the property of the fiber is much higher than the epoxy it is being embedded. Okay, so. And for example, to compare, you can do quasi-static indent. We've done these indents at different locations, A, B, C, D. This is the low displacement response at different locations. And from this low displacement response, you can measure the modulus. And in comparing the storage and loss modulus with respect to quasi-static technique that we already know, which works very well, compared to this imaging technique, you can see that it correlates very well. So this particular technique works very well, and then you can get property as a map. Okay, so that is the power of the technique. With this, I'm kind of getting up to talk about high temperature applications, how measurements can be done at high temperature. This is very important because when I talk about high temperature, it's very important to recognize that when you heat up something, you have thermal expansion, right? Typically metals, when you try to heat, per degree centigrade increase in temperature will give you about microns of displacement. So in such a situation where per 1 degree Celsius in change in temperature will kind of give you in micron displacement, it's a challenging kind of a situation. You wanted to measure the property of at nanoscale. Okay, so thermal drift is a huge problem when you try to measure property of a material as a function of temperature. How do we solve that? So in this particular, we worked on this problem for almost 10 years to figure out how to do this properly. So we developed a unique heating stage, and this is the heating stage that I'm schematically showing over here. It has two parts, the top part and the bottom part you can see. And the top part has a heating coil, and the bottom also has a heating coil that heats the sample. So you sandwich the sample between these two heaters, the top heater and the bottom heater. This top heater also kind of clamps the specimen. You don't need another clamp to clamp the specimen because when you try to use another clamp, it is also sinking the temperature. Okay, to avoid that, we can use the top heater itself as kind of a clamp, and it is gravity loaded. So it kind of sandwiches the sample in between the top and the bottom heater. And it also helps in a way that you can heat the sample from the top as well as from the bottom. So it kind of eliminates the temperature gradient across the thickness of the sample. Okay. And the third thing is, like, if you're having an O-ring like this, you can create a kind of a micro chamber, and you can keep an atmosphere within the chamber, whatever the atmosphere you want. So for example, when you try to do on a material like metals, which are very sensitive to oxygen, when you try to heat up, it will oxidize the sample surface. By passing in inert gas, you can avoid that. So by creating a chamber, small chamber, and passing an inert gas, you can control the oxidation of these metals when you try to heat them. So it's kind of a unique micro chamber, micro heating chamber design. And by the way that you are heating from the top as well as bottom, you are able to kind of avoid the thermal gradient. And the third important thing is, in this whole structure has been designed in such a way that thermal expansion of one material kind of cancels the thermal expansion of the other material. So the net thermal expansion is only about 6 nanometers per degree rise in temperature. So I'm going to straight away going to go to these slides. This is an example that I mentioned, that if you pass an inert gas, you can avoid. Without the inert gas, you can see here in the copper sample, it's completely oxidized. On the right side, you can see it's the oxidation is very less. So it kind of avoids the oxidation by using inert gas. So it's possible with this particular design. Okay, and then I mentioned that you can also heat the sample as a sandwich, and so the kind of thermal gradient is very less. So this is one particular example that I'm kind of go and give you. Here, this is for silicon carbide fiber embedded in a silicon carbide matrix. And these experiments, we were able to do up to 1000 degrees C. This particular example is only 400 degrees C. And here, like each can small indents, and you can see that here is a matrix of indent. And from that, the hardness of the material at 400 degrees is being measured, which is plotted as an image. And we were able to do that up to 1000 degree now. So this particular heating stage kind of allowed us to kind of go up to 1000 degrees C, and you can also do it at precisely and without any problem of drift. Okay, and this is just kind of an example that I would like to give. Okay, so with that, now we can go on to this particular slide I already presented for polycarbonate. Now we can go and heat the samples, and we can also change the frequency. Now with that, we were able to get this time temperature superposition. You can see that this particular curve has there are different curves, and the top curve is the storage modulus as a function of temperature. And you can see also at different frequencies. So the blue curve is at low frequency, and as you go, the red curve is for the higher frequency. and from 10 hertz to about 300 hertz, you can see as you change the temperature as well as change the frequency, the property of the material is changing, the storage modulus is changing. The bottom curve is for the loss modulus. You can see the loss modulus increase and decreases. You can also see the peak. Okay, so by measuring the frequency response at different temperature, we're able to measure the response of this material, and with this we can even construct a time temperature equivalent response on this material. This is very useful for polymer chemist. Okay, now this is another example. This is for PET thin film 100 micron, whereas you can heat the sample and continuously measure the tan delta by taking the ratio of the storage modulus to the loss modulus and measuring the tan delta as a function of temperature. For example, you start with 25 degrees centigrade and heat up to 175 and then cool down to 25 degrees centigrade. So throughout this temperature cycle, you measure the tan delta as a function of temperature. From that, you can also calculate what the glass transition temperature is. And you can do it for in thin film. So this is the only way now you can do if you wanted to measure the glass transition temperature of thin film. This is the only way that you can do. In bulk DML techniques, you won't be able to do that. So that's another example. So one more example of that I would like to give before I start is creep measurements. Creep is very important for high temperature materials. So now because we have a way of heating the samples, and also I mentioned about this dynamic measurement technique, by combining these two, we were able to do experiments on metals, even temperature as high as 1000 degrees, and we can even do measurements, creep measurements for hours. Without having problem of measuring the drift. So in this measurement technique, you need to know how this is being done. So in a typical inundation experiment, the way to do is you measure the, for example, you load the sample to a maximum load and try to keep the load constant and measure the displacement response of this inunded tip as a function of time. Then you measure the displacement as a function of time at the maximum load, and from the measured displacement as a function of time, you can measure the strain rate that is being imposed onto the material by simply taking the differential response. For example, if you take the dH by dt and divide by the depth h, that gives you the strain rate. This is how it's been measured with inundation technique traditionally for many, many years. Okay, but the problem in this type of measurement technique is, along with the displacement, the true displacement response of the material, you also measure the thermal drift response of the system. So it's very difficult to kind of separate the drift from the actual depth of penetration that you wanted to make a measurement and measure the strain rate. So, but if you do a kind of a dynamic measurement technique where you measure the stiffness response as a function of time instead of displacement response as a function of time, it kind of gives you an edge over thermal drift. Now, you're not monitoring the depth of penetration, but you're monitoring continuously how the contact stiffness is changing or how the contact size is changing as a function of time. And this has been done at a higher frequency. It's not done at lower frequency. Thermal drift is a low frequency phenomenon. Because it is done at higher frequency, you kind of a cheat, and then you don't need to worry about the thermal drift. So even in hours, like if you can keep it for many, many hours, you will measure the response without any problem of drift. This is what I've shown here in this next slide, where the red one is the measurement done through a displacement measurement technique, displacement as a function of time. And then if you try to measure the dH by dt, it is 0.097 nanometers per second. This is not bad, but over a period like 3,500 seconds, you have about 400 nanometers of penetration. It is purely due to drift. Okay. At the same time, you try to measure through the stiffness measurement technique over this whole 1 hour period, you can see the drift that the dH by dt that you measure is only 0.008 nanometers per second. It is ridiculously small. So what it means is basically the measurement that you have done by measuring the stiffness measurement technique is completely insensitive to thermal drift. So you can use this dynamic measurement technique to measure the stiffness as a function of time. That allows us to measure the creep properties of materials. And you can also even measure the thermodynamic quantities like activation energy. So how it can be done? Instead of measuring the depth as a function of time, this is particular example is for polycrystalline copper. These experiments were done from 400 degree to 600 degrees C. You can see how the contact stiffness is varied as a function of time. And this is done at a particular load. Instead of measuring the depth, you measure the stiffness as a function of time. And from the measurement of stiffness as a function of time, you can calculate the hardness as a function of time. Now you can fit this stiffness as a function of time curve, and you can differentiate, and you can measure that S dot over S, basically ds by dt over S, and that gives you the strain rate. So you can measure the strain rate by fitting this curve. Similar to S dot over H, you can do S dot over S. And by measuring the strain rate as a function of time, and also measuring the hardness, basically the stress. Hardness is nothing but the mean stress. You can measure the stress as a function of time. You can measure strain rate as a function of time. Using that plots, if you plot the strain rate versus stress, you can kind of you can use Arrhenius plot, and then from this measurement, for example, if you plot strain rate versus stress, you can, from the slope of this curve, you can measure the stress exponent. And in this particular case, the slope is about 7, which matches with the bulk measurement technique. And then if you do it at a constant stress, for example, the stress is constant over here. And if you plot in those kind of situation where the stress is constant, but you plot strain rate as a function of 1 by RT, the slope of the curve gives you the activation energy. So in that way, you can also measure this thermodynamic quantity pretty accurately by doing at different temperature, but directly doing with this dynamic measurement technique. So this is for particularly for copper, and that kind of it matches with the activation energy for lattice diffusion, which is about 197 kilojoules per mole for copper. And we repeated this for different material. For nickel, also it matches in a similar measurement technique where you measure the strain rate as a function of stress. And then at the constant stress, you can plot strain rate versus 1 by RT. The slope will give you the activation energy. So I think I'm pretty much closer to my time limit. So I will stop here and then take any of your questions. So Pratyang, over to you.
Yeah, thanks. Thanks, Dr. Asif. Pretty interesting talk. So I've got a few questions lined up. First question from Sujata. She's asking, she wants to know what are the basic information that we should keep in mind while performing nanomodulus mapping on porous ceramic coating. What are the other characterization we can perform on metal ceramic composite using nanoindentation instrument?
Okay, it's a good, interesting question. The parameters that needs to be kept in mind if you try to do modulus mapping or any dynamic measurement technique is, this is what this is a question. The force amplitude that you apply has to be very, very small. For example, you're trying to keep contact on the sample surface. And if your oscillation amplitudes of micronewtons or many micronewtons, you're basically jumping on the surface. Basically, you're kind of hammering on the surface. That means that you're losing contact from the sample surface. So the force amplitude that you apply is very, very small. It will be nanometers. And the displacement response also in less than nanometers. So this is kind of a small signals. And you have to use locking-based detection technique. Normal detection technique won't work. So that you need to keep in mind. The amount of force that you are applying is very, very small. The displacement responses will be very small. It is very difficult to make a measurement unless you use a lock-in detection technique. So that is very important. The second thing is that when you are scanning, you have to do a very slow scan. You can't do in an imaging technique, we can scan at 1 Hertz, 2 Hertz, and 5 Hertz. But when you try to do a modulus map, you need to scan it very, very slowly because kind of averaging over an oscillation amplitude, right? If you try to move very fast, you're moving from one place to another place. Before you get that average, you are going to the next place. So you have to do it very slow. So this is going to be a slow scanning technique. Typically we do zero point 0.1 hertz, even less than that. Okay, so those things are very important. The third thing is the surface roughness. For example, if you have a huge surface roughness, when you try to scan, the tip may jump from one location to another location. That will kind of gives you some false stiffness measurement technique. So it should be smooth, it should be well polished. So if it is well polished, then you don't have any problem. If it is rough, you will have this error due to tip jumping from one location to another location. These are all the things that you need to keep in mind when you do this modulus mapping. What is the second question?
What are the other characterization we can perform on metal ceramic composite using nanoindentation instrument?
So other than, I already kind of in the first webinar I mentioned about measuring fracture toughness. Okay, you can do that, and by measuring the crack length. That other than harness and modulus, you can do that. In this presentation, I mentioned about you can measure the dynamic properties basically, and along with that, you can also measure the creep resistance. And so the dynamic measurement technique that I presented today is a very, very sensitive measurement technique, okay? Because you're measuring stiffness as a function of time. And let's say you can measure a stiffness about 10 newtons per meter is basically stiffness of your atoms in contact, okay? So that is the kind of high resolution you can go. If there are diffusion of few atoms in contact, you are able to measure that. So even for material like ceramics, tungsten, which we believe that they don't creep, actually you can measure creep, okay? So you can measure the creep response of these materials as well. So these are all the things that you can measure. On porous materials, you can measure the densification. As you apply the stress, how the material is densifying, you can measure that. So there are a lot of things you can do with the nanoindentation technique beyond harness and modulus measurement.
Okay.
Okay.
Yeah. Property mapping, like stuff to do the composite.
Yeah, so you can do the property mapping, but it's all about elastic response. When you try to do with this modulus mapping, it's all about elastic response. If you want to know the plastic response, you have to do a plastic indentation, in which case you need to do this high throughput indentation that I presented in the last webinar. You can use that to measure the harness as a map as well.
Yeah.
But if you try to do modulus mapping, it is only about elastic response.
Yeah. So the next question that I have from Yanan Zhu, sorry if I pronounce it wrong. The question is, you want to know how to get stress and strain information from nano DMA data?
Well, stress is load divided by area, which is basically your harness. Okay, mean stress. We call it mean stress. Okay, and strain is basically displacement, right? So, and for a given geometry with the indentation technique, depending upon the geometry, you are putting different strain. Okay, for example, when you use Berkovich, the included angle is about 136. You can calculate what the strain that you are putting. If you use a cube corner, which is about 90 degrees, you put higher strain. So the strain changes with the geometry. But if you use a spherical indenter, A by R ratio kind of gives you the strain. The load divided by area gives kind of the stress. So you have to convert the load and to stress, and then the dispersion to strain.
Yeah. So normally we use spherical probe, right, to get the stress strain.
Yeah, you can use a spherical probe if you want to continuously measure the stress strain response. But you can also use different geometries. For example, in the old days, we used different cone with a different cone angle. And this is not a kind of the same stress strain relationship we talk about in uniaxial stress. This is kind of equivalent strain, okay. Because under the indenter, the stress state is very complex. It's not uniaxial. It's a very complex. It's 2/3 hydrostatic, 1/3 shear. Okay, but we can kind of equivalent strain. We can okay.
Okay, so another question from the same person is, could you please give some suggestions on the key parameters need to be considered or adjusted to get good nano DMA data? I mean,
Okay, the important parameter is the force amplitude. I already
Yeah,
answered that. And then the displacement amplitude.
correct.
And it cannot be too high, it cannot be too low. If it is too low, sometimes you won't be able to make a measurement, it will be too noisy. So it's kind of a key, we use certain
Normally,
percentage.
we keep 2 to 4
Yeah.
nanometer. I mean, again, depending on the material response, but 2 to
And
4
depend upon the
nanometer.
depth you go. Also
Yeah,
depth you go. Yeah.
correct.
So that comes with a little bit experience, depending because material is different. So it kind of a learning curve. When you do 1 or 2 experiments, you pretty much know what is the right setting for that.
Yeah. So Yandu, I mean, I also suggest him like you can reach our application team. Also, it seems you have our instrument, and if you want to further improve your data, you can always feel free to reach our regional application team, or you can drop me a mail. I can also help you to in this regard. So I'll move to our next question that we have from Indrajit Kumar. So what change in instruments we need to do in room temperature nanoindentation setup to perform high temperature creep testing?
Okay. First of all, you need to have that high temperature exhaust heating
Yeah,
stage. And I mentioned clearly, like it's a unique stage. It's been designed in a mind where the thermal drift has been taken care of. The thermal expansion per degree rise in temperature is only 6 nanometers per degree C, and it is a kind of a micro chamber. So you have to have that heating stage first, and that's very, very important. Second thing is you need to have a DMA measurement capability in the instrument. If you have both of that, you can do high temperature creep measurement without any problem.
okay. Yep. So can DMA be used for both metals as well as non-metal?
Yeah, DMA can be used for polymers, ceramics, even biomaterials.
Yeah. At high temperature, do we need to? Okay, so another question: at high temperature, do we need to change the indenter tip or same as room temperature? Yes, we need.
Now, high temperature, depending upon the material you use, you need to change the tip material. Okay,
Yep.
sometimes you use sapphire, sometimes you use diamond. So if you use steel, you don't use diamond because you will lose the tip because of diffusion of carbon. So in such case, we use the sapphire tips. Sometimes we use silicon carbide. So depending upon the material you use, the tip material will be different.
Sure. Okay. Yeah, I think one more question I have: how to decide the maximum load for a material?
How to decide the maximum load? It depends upon like what you want to test. I mean, if you have thin film, you have to limit your load because you want to measure the thin film response. You have to apply very small load so that you are on the thin film rather than on the substrate. So those things are important with respect to how much load you can apply, and that's I think only condition that I may think of. Otherwise, like if the material allows you to load, you just go load. If you have the
Yeah.
capability to apply the load.
Sure. I think with that, I think we've got. Okay, sorry. One more question from Swati. I think we'll take one more question. It's in case of UTM, we can get the average value of elastic properties. Comparing this with nano indentation, we can get the properties of each different phase of multi-phase material. So how can we compare nano to UTM, nano indentation to UTM? I think it's
Okay, so like for example, in the last, I don't know whether I did that in the last webinar. Let's say you have a multi-phase material, and then you are doing like 1,000 indents, right? So in that 1,000 indents, is basically it covers both the faces. Let's say you have 2 faces, okay? So that gives you in a square array, you're doing 1,000 indents, which kind of covers 2 different faces. And if you take all these measurements and if you take a histogram, it will give you the distribution, kind of bimodal distribution, depending upon the phase distribution is. So, okay. So that kind of allows you have now, for example, if you have 2 phase materials and you have 2 modulus, then you can use this composite technique to measure the average modulus, right?
yeah.
Now, that's one way you can kind of quantify. And that allows what is the contribution of the second phase with respect to the first phase. That's what it helps. And if you do like a micro indentation technique, maybe you will get the same thing, but it doesn't give you that kind of a resolution and clarity compared to when you do thousands of nano indentation on the same area.
So we have got to. Are you okay? So I'll just take.
Yeah, I'm fine.
Okay.
Keep going.
Okay, so it looks pretty interesting topic today. So a question from Rubia, she's asking if cracks are induced during indentation, are the hardness and modulus values which we get correct in that case?
No, it is not, because I think some amount of energy that you are putting into the system has been relieved as a crack. So in that case, you're going to have some error in your displacement response and or the force response. So it will not be the same. So if when you have a crack, it's going to take the energy being dissipated in some other way, right?
Right.
So the cracking is going to change how you measure the properties.
Okay. So the next question from Anand is, can possible to check at lower temperature, example minus 30 degree?
Yes, we do have cryogenic stage that allows you to do at minus 30 degree easily.
We can go minus 120.
120, yeah, 120.
Yeah, minus 120 to 2. We can in the cryogenic stage. So we can do experiments at minus 120 as well. Okay, I think that's where.
Okay.
Okay, sorry, one more question to follow up. The average modulus obtained from nanoindentation of two-phase material will also have a high standard deviation. How can we compare with UTM? I think that's
well, that kind of gives you what is the role of this microstructure, right? That's what I'm trying to tell. And I don't know how to compare with UTM, but it gives you clarity on the UTM measurement that you did. What is the contribution of these phases in terms of statistical distribution? That is what it does. Maybe you need to develop a model to kind of compare with the UTM measurement that you, but it gives you the data to do that.
Right. So I think that have answered plenty of questions from everyone today. And with that, we'll move towards a concluding session for today. So I would like to thank all attendees for sparing time from their schedule, and definitely very interactive session at the end. Please also note to register for the upcoming webinars. There are separate links actually. So the same link won't work. So please go. I mean, if you haven't registered separately for the upcoming webinars, please do register. It will be further interesting talks as we'll be discussing more on the in situ techniques that include a scanning electron microscope based nanoindentation technique and transmission electron microscope based. If you have any further queries, please feel free to reach me at pratyank@industronnano.com. And yes, the recording of each session will be uploaded at our YouTube channel, and I will be sharing the link with all the participants who have registered and even who have missed to attend. So they will get the recording of the session. So then stay safe and hope to see you in the upcoming webinars. Take care. Bye.
Yeah. Happy Thanksgiving to everybody.
Yeah, thanks. Yep. Sure.
Okay. Bye-bye.
Bye. Bye, everyone.